All right, so we are actually on lecture number 18, and we're going to deal with the complex integration. In the last lecture, I dealt with integration that was path dependent. So recall that when we do the integral of a complex function, it's like finding integral of f of z dz, which actually boils down to the integral of u plus I v, and dz is dx plus I dy along some path. So in fact, if you had to expand this, you will get u dx minus v dy plus I integral of, now there will be v dx, and on the outer side you have u dy plus u dy. In other words, a complex integral is a line integral. It's actually sum of two line integrals. These are line integrals. So in the last lecture we came across what we call path dependent. So let's take an example from the last lecture that is very similar to this here. Here's my example. Somebody rearranged the pages. Oh, it looks like I have the wrong pages. Okay, it doesn't matter. I think it was the integral of bar z over z dz, where the path gamma is the Archimedean spiral. Given by x equals to t cos t, y equals to t sin t, and the parameter t varies between 0 and 2 pi. So you want to find that integral there. So if you draw a picture of the Archimedean spiral, which you're not supposed to know really, I don't expect you to know it off, from some memory. So generally, if you set a question like this in an exam or a test, we'll give you the picture, or it'll be something we've done before. In future, we can speak about an Archimedean spiral because you've now seen it. But it is something like this. It carries on many times, but I'll stop it at 2 pi. So the parameter t starts at 0 and goes up to 2 pi. So we must now calculate the integral. So we use a parameterization. So z here is t cos t plus I t sin t. That's like t cos t plus I sin t. Or it's t e to the I t. Cos t plus I sin t is e to the I t. That's Euler's formula. Now I need to obtain dz to compute this thing. Dz will be derivative of this. T times the derivative of e to the it, which will be e to the it times I, plus e to the it times the derivative of t, which is 1. Then just make this look a bit better. It is 1 plus it to the times e to the it. Is that right? dt, sorry. I should say dt as well. Okay, let me say dz dt. And then z is t e to the it, bar z will be t e to the minus it. Or mod z. It will be mod of t mod e to the it. Mod of e to the it is 1, so it's just t. The mod of e to the it is 1. It's like sine squared plus cos squared. Square root of sine squared plus cos squared t is 1. And the t in front is the square root of t squared, which is just t. T is positive here. So that's enough now for me to compute the integral. So when I compute the integral of mod z, a bar z over z dz along gamma, it can be written as mod z is t over z is t e to the it times dz is 1 plus it e to the it dt. I just plug in all the stuff over here, including dz, which is now something dt. Then this guy kills that guy, this guy kills, hey, what? Almost everything dies there. And so this thing becomes, of course, the limits are not to 2 pi because now we are in the t world, no more in the z world, we are working in t. So we can now integrate this straightforwardly, t plus it squared over 2 from 0 to 2 pi. Right, and then you can get a certain answer here. 2 pi plus 4 pi squared over 2 is 2 pi squared I. There's 2 pi into 1 plus pi I. That's the value of the integral. If you go on an Archimedean spiral, t cos t, t sin t. You see, it's not a real number. It's a number with I in it. Therefore, I can't give it any characterization as some like an integral being an area or so. It's actually the sum of two line integrals, in essence. Now, let me change the path. Let's use a new path. Let's take the path, same spiral, sorry, but let's go from, let's change the path from 0, 0 to 2 pi naught, the straight line. You go with a straight line. In other words, I'm talking about this piece of graph here. Suppose that's the path. Now, what's the parametric equations for that path? For the spiral, it was t cos t plus I t sin t. What about for a small piece of line? Well, you don't need a parametric version, but if you want to have a parameter, you can say x has some value, so x can be t, and y, of course, is 0, because there's no height. It's not moving on the straight line. X is some t value between 0 and 2 pi. T belongs to 0 and 2 pi. So that's what the parametric representation is. So if you want z, which is x plus iy, which will be t plus naught I, dz will be equal to 1 dt, and mod z will be the square root of t squared, which is t, again. So the integral of mod z with z dz along this new path, gamma 2, will be the integral of t over z is also t. Dz is 1 dt. Now it's from 0 to 2 pi. It's the integral of 1, basically, which is t. You can see that answer is 2 pi. Whereas this answer here was something else. 2 pi times 1 plus pi I. The answer here is just 2 pi. So, moral of the tale. The moral here is that the value of integral depends on the path taken. In other words, it's path dependent. It depends on the path. Path dependent. Obviously, you're now asking yourself, since I made that claim, you want to know whether is it possible to find an integral that is path independent. Can you have an integral where it doesn't actually depend on the path? Any path can be taken, you get the same answer anyway. Can that be possible? Is it possible for that to happen? The answer there is yes. And for that to work, we milk Green's theorem. Does that ring a bell to you? Green's theorem for Maths 212. Double integrals can be written as a line integral, and triple integral can be written as a surface integral. The Stokes theorem. You must have done that in 212 and 251. It doesn't matter if you haven't done it, you can't remember it in detail, but the essence is that it's Green's theorem that we will be using here. So I haven't got my problems here, but anyway, I'll just make it up as we go along. So let's start off. We'll call this the Cauchy-Gaussat theorem. Say we have two functions, p of xy and q of xy. That are holomorphic. In a connected region D. Region D. Here it means there's no holes. So a connected region is like that. There's no sections that are removed from it. There are no holes. Then you find day P, day X will be equal to day Q, day Y. Now this, where am I getting this from? So let me then delve into the Green's theorem. This comes from Green's theorem. I should have had the full statement here. See, I didn't have the Green's theorem tells us that the line integral p dx plus q dy can be written, so you can have any path there, is the double integral over an area qx minus py, day q dx minus day p dy. So this is a mistake. This should be other way around here. Day p dy equals to day q dx. Sorry, correct that. That's a mistake. Day p day y equals to day q dx. Dx dy, this is over some area. That's Green's theorem, which we have seen in the second one. So you can see that if this happens, then this part becomes zero. Well, that's what it really is. It's simply the double integral of a over a, day q day x minus day p day y, dx dy, and this will be zero. So this means that f of z, the integral of f of z, okay, let me write this nicely. This implies the integral of f of z dz is path independence. That's known as the Cauchy-Gaussat theorem. If you have the Cauchy-Riemann equations working, then day p day y equals day q day x. By Green's theorem, it means that the line integral is path independent. That's Green's theorem. As a corollary, if you have a simply connected region like this, and you have 2 points A and B, and two paths going from A to B, but in two different paths, let's say. Then in the region D, in D, you would have the circle integral of f of z dz equal to 0. Proof. So you can say the integral, so from A to B, the line integral from A, let's call this 1 and 2. Line integral from along 1 of f dz minus the line integral from 1 along path 2 f dz, this would be 0. Which implies that because they give you the same answer, if you take this guy on that side, you get the same answer. I'll just transfer this guy onto the left hand side. And you can think about it by saying integral f dz along 1 equals integral f dz along 2. That's what we mean. The path integrals are the same answers. So I've just transported the 1 across because I want to massage it to look like a circle integral of f dz, which is 0. That's an offshoot of the Cauchy-Gauss theorem. Cauchy-Gauss theorem tells you if a function f satisfies the Cauchy-Riemann equations, then the integral is path independent. That's the model of the theorem. And that's the consequence of Green's theorem. Now we will test it. Basically, we proved it using Green's theorem. But in case you don't fully understand how it works, we'll test it with some examples. Any questions thus far? I can't remember the example. I think it was 1 over z. Anyone has a book there with them? The book. Here's the book here. It's better to use the example that's there, otherwise you can confuse. The one that's here has log in it. That's why I like to do it. I think it's 1 over z. Okay, here we are. Now we are close. By the way, guys, we are going to finish chapter 2 this week. We're going to do Cauchy's integral theorem on the next lecture, and that will be the end of chapter 2, which means that all the TUT problems are relevant and they will be set in the test on Tuesday. So you've got to work through them all. I don't know why it was that you were not there yesterday. What's the reason why you were absent yesterday? Huh? Test. Huh? Clash. What clash? You can't have a clash. That's maths period, man. Oh. It is your normal period, guys. Everybody. That's the part I'm not getting. Because that TUT period is can be valuable. You know, you have to work through the problems there, and then you can ask for help. What's happening here? Why do things work slow? This tells you it's much better to have the book than to have the software. Yeah, you see, these are the TUT problems. Cauchy-Riemann equations. You need to practice them. Find the real and imaginary part of that. Expand it. Give it a function, show it is harmonic, and find the other one that makes it holomorphic. Those are the typical questions that will appear in the test. Okay. I don't know where the thing is. The trouble is, this is reacting like 10 minutes after me. Anyway, let's make up a problem. Example, let's say find the integral of 1 over z, where z is the Archimedean spiral from, let's go from z equals to 2 pi to 8 pi. Something like that. That was the problem. Along the path gamma. The trouble with choosing an arbitrary example is that it ends up not working. Yeah, this is where we are at. Okay, there's a very simple example there which I'm not going to do. That is z to the fourth. Ooh, I wish this thing could stand still. Look at this. How am I supposed to do this? God. I want to see the, was it? Hey, I can't see the example. It just goes past me. Shit. Well, there's this easy example here, which is z to the fourth. You see, if you look at the book, look at the board, there's an example of z. Hell is going on? I'm doing nothing. Hey. Anyway, okay, let me just conclude the point. I wanted to actually show you that you get the same answer for both parts. But if I choose a lousy one, then it doesn't work out nicely. The integration doesn't work out nicely. Anyway, let's see what happens. You take z equals to t cos t plus I sine t, it sine t. That's t e to the it. And so dz works out 1 plus it e to the it. So then we get the integral along gamma 1 over z dz works out to be the integral of 1 over t e to the it from 2 pi up to 8 pi. And then times dz is 1 plus it e to the it dt. Okay, now this should work fine. Then this gives me, so these things cancel off. I end up getting the integral. So I've got to divide by a t at the bottom. There's still a t here. Oh, I should have put this light off. 1 over t is 1 over t plus it over t is I. So it's I dt from 2 pi to 8 pi. And now we are in the simple integrals. So integral of 1 over t is ln t plus it, and the limits are from 2 pi to 8 pi. So this gives us ln 8 pi plus 8 pi I, substituting the 8 pi first, subtract ln 2 pi plus 2 pi I. Ln 8 pi minus ln 2 pi is exactly ln 6 pi. I mean 4 pi. Because you divide, eh? When subtracting logs, 8 pi divided by 2 pi is 4, not 4 pi. It's just 4. Ln 4 plus 8 pi minus 2 pi is 6 pi I. Alternatively, you can write that as integral of 1 over z dz equals to log z. Isn't that the integral of 1 over z dz? It's log z. And this is ln magnitude of z plus I argument of z. Remember this expansion of log z? Log of a complex number is ln of the absolute value, or the norm, plus I argument of z. And you can carry on working this problem out using 0 to 2 pi up to 8 pi, and you'll get the same answer. So the point of this theorem is that, or the moral here, if f of z is holomorphic, meaning it satisfies the CRE, then the integral of f of z dz is path independent. You'll get the same answer irrespective of which path you choose. So, integrate as for normal functions, as for real valued functions. So if you take the example of z to the 5 dz, if you get an example like this in the exam, and the path here is, so gamma goes, gamma is the circle at 0, 0 with t from 0 up to 2 pi. That information is totally useless. That part there is not important because it's path independent. It doesn't matter what the path is. You can choose any 2 paths, any 3 paths, 4 paths, all the answers will be the same. It will boil down to, this becomes integral of z to the 5 is z to the 6 over 6. Isn't that the normal integral that you came across in first year? So we have to say what the limits are. Let's say 0 to 2 pi. You put 0 there and 2 pi. You have to specify the starting and ending point. That's all. The path it takes is immaterial. If you know the start and ending point, then the answer is 2 to the 6 is 64 pi to the power 6 over 6. So that's the answer. There's no I involved. It's a straightforward calculation. Any questions? So the trick is to realize if the function you're dealing with is holomorphic or not. How can you check if it's holomorphic? I mean, how can you really test if it's holomorphic? What? No, how do you test if the function is holomorphic? You satisfy the Cauchy-Riemann equation. Qx will equal py, px will equal minus uy. If you know it's holomorphic, then you can integrate it like that. Ignore the path. Sometimes in the test or exams, we are the testing. We give you the path. And some poor handlers that actually uses the path and calculates it. You get the right answer. You must get the right answer because we are saying it's path independent. So it doesn't matter whether you use the path or not use the path. But might be the question here is 2 marks, like that there. It could be 2 marks. And the poor guy calculates it on the page and he gets 2 marks. And then but you know what the complaint comes in? The student will say, no, but your test was too long and unreasonable. You say, but look, you, a 1-liner or a 2-liner, you took 10 pages to do it. It's not our fault. So you should realize you're dealing with a holomorphic function, and then the integral will be path independent. Of course, you're thinking, how do you know how to detect? Let's write in a few notes on this. How to detect holomorphic functions. You don't always have to hit it with the Cauchy-Riemann equations. So we know they satisfy CRV, but some of them you can check visually. So polynomials are holomorphic. Right, example, z to the 5 plus z cubed plus 2z. That's a polynomial, it will be holomorphic. Then your trig functions are also holomorphic. E to the z, sine z, cos z, log z, except at, anyone remembers? Where is log z not differentiable? Origin, except the origin, log z. And cosh z, all of these functions are holomorphic. Sinh z and tan z and so on. They're holomorphic. You don't have to test them. You don't have to check the Cauchy-Riemann equations. You can accept that they are holomorphic. Then you also have rational functions. These are also holomorphic. Example, sine z over 2 cosh z plus 1. Sine z is holomorphic, this guy is holomorphic, rational will be holomorphic. You can take that to be a fact. Then you also have composition of functions. So you can have, if f is cos z, g is log z, and h is e to the z. So e to the, well, this, okay, 1 plus e to the z. Then if I do f of g of h, it will be cos of log of 1 plus e to the z. That would be holomorphic. It's a composition of all those functions. Okay, so now we've completed chapter 2. That's the end of it. It's Cauchy-Riemann equations and the consequences thereof. To recap, if two functions are, defining a right integral, a complex function, generally it is path dependent. Okay, we should actually write here which ones are not holomorphic. We have done this one before. Which are the ones who will be a dead giveaway which are not holomorphic? One? There's only two classic ones. One is, yes? Yeah, I don't know, sometimes whether you guys go for what, but you are not following at all. And the other one is bar z. I must have said that by 20 times in the course of these lectures. Bar z and mod z. If you see that in combination with anything, it's not going to be holomorphic. So other than that, all these guys here are going to be holomorphic. So in the tests and exams, and also tutorials, if you look back at the book, hopefully we can get a still picture of the book. You'll find that the examples are like that. Find certain integrals. This is a bit ahead of the game. Calculus of residues. This is the next beautiful chapter 3. Oh, here we go. This is the stuff we did today. Cauchy-Riemann equations. And then this next chapter here on complex differentiation. This is moving too fast already. Under this Cauchy-Riemann equations, guys, you'll find that the examples are like what I discussed here. I don't know how to explain this, but this is just doing its own thing. But the first set of questions says, find the following integrals, and it gives you a path. The second one says path independent. Those ones you just integrate and substitute. The first one you have to do parametrization. And the familiar parametrizations are the circle, which will be cos t sine t, the spiral, which is t cos t, t sine t. You also have the hyperbola, which is sinh cos t minus I sinh t. But it's given there as an example in one of the previous examples. So I think you should work on those problems, and on Monday we can discuss them. But in the next lecture, I'll finish up the chapter with the Cauchy's integral theorem. That will be the end of this chapter, and we move on to the calculus of residues. I will stop there. Computer has gone bonkers here. Yes. No, Thursday. But you know you have to go up to these this week's work. But I'll clarify whether Marisburg has reached the same point. I need to speak to Marisburg. That's it. Not you guys. You guys, I can make any points. Yes. 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 The people. What the heck, man? How can I get this simply wrong? Yes, what is your question? Oh, okay. See, the original dates were this. The original dates were Wednesday, 17 April. But that's 2019. Hey, this is crazy. It means this was originally correct. This is a Tuesday. Okay, I'll publish another correction of that.